Hello everyone, hope all you have watched the video where I have shown the standard hydrogen electrode. Now that was the primary reference electrode, and today in this lecture I will introduce you the secondary reference electrode. Now what is the necessity of using different types of reference electrodes? That is the purpose of this lecture, and also we will know the details of Calomel electrode, which is mostly used secondary reference electrode. Now before using secondary reference electrode, one may have a query that what is the problem with the primary one, that is with the standard hydrogen electrode, what is the problem? So before going to the limitations of standard hydrogen electrode, that was the primary reference electrode and has been discussed in lecture 11, first you have to know that what are the criteria that makes an electrode to be used, to be taken up as reference electrode. That must be one's query. So criteria that makes an electrode acceptable as reference electrode. So first point is that it must exhibit constant electric potential. For small withdrawal of current, that electrode must not fluctuate its potential. So it must exhibit constant electric potential. We will measure the EMF using a potentiometer. So we are not going to draw even a small amount of electricity, but there are experimental limitations. There are limitations from the experimentalist. So even if a small amount of current is withdrawn, then there must not be fluctuation, and if it occurs, it cannot be granted as the reference electrode. So the first point is it must exhibit constant electric potential. Now secondly, it must be reversible and must obey Nernst equation. So the reaction that is occurring within that half cell must be reversible, and we must be able to apply Nernst equation without any hesitation. So there are no problem in using Nernst equation for that electrode. And the third point is it must be easy to construct and easy to maintain. So if you find any single electrode which satisfies these three criteria, that is, it must exhibit constant electric potential, Second point, it must be reversible and obey Nernst equation, and it must be easy to construct and easy to maintain. Then it qualifies for acceptability as reference electrode. It qualifies for reference electrode. Now, SCE exhibits these two factors efficiently. So, SCE, that is standard hydrogen electrode, which was the central topic in the previous lecture, lecture 11, that is the standard hydrogen electrode, obeys 1 and 2 strictly. That is why we have used it as the reference electrode, but its construction procedure is not that easy, and even if we able to construct it, handling such single electrode is quite difficult. And also there is another thing, it is not easy to maintain. So, that is why a need for a secondary reference electrode came into the picture. So, we need a secondary reference electrode which will obey all the 3 points, that is, it will exhibit constant electric potential, it will be reversible and obey Nernst equation, and that will be easy to construct. If it is not easy to construct, no problem, we will construct it, but maintenance must be easier. Since students are going to handle it, any laboratory apparatus, any experimental apparatus must be maintenance easy. So, we need a electrode which may be difficult to construct, so that there are companies, there are enterprises which will build it and will sell to the laboratories, but that must be easy to maintain, since you are going to maintain it, students are going to maintain it. So, we need a second option rather than standard hydrogen electrode, and that is why we need Calomel electrode. So, it is not the case that we are satisfied today with Calomel electrode. There are several sub reference electrode that have been evolved as per requirement, but we will restrict ourselves only to the first kind of secondary reference electrode, which is the Calomel electrode. Now, Calomel electrode exhibit constant electric potential, it is reversible and it obeys Nernst equation, it is almost easy to construct and leave it, but it is easy to maintain. Now, another problem which is incorporated in the SCE, which may be considered as the limitation. So, the limitations of SCE first limitation is this one: standard hydrogen electrode is not easy to maintain, but for what? It's not easy to maintain 1 atmospheric pressure of hydrogen in 1 molar electrolyte. So, you have to maintain 1 atm pressure of hydrogen in 1 molar solution of H plus. So, it is not easy to maintain this pressure of this gas and the concentration of H plus ions. This is one problem, maintenance is not easy. Second problem is that any impurity present in the gas or in solution can poison the functioning of any impurity present in the gas or in solution can poison the functioning of platinum electrode. Since platinum electrode is impurity sensitive, you have all heard of the reaction that is involved in the contact process preparation of sulfuric acid, that is oxidation of sulfur dioxide to sulfur trioxide, and that oxidation is being carried out in presence of platinum asbestos. And you can remember that before taking the gases sulfur dioxide and oxygen in the proper stoichiometric ratio to the reaction chamber, they are being properly checked with the property Tyndall effect that it must not carry any dust particle with it. So, if there are any kind of impurities present within sulfur dioxide gas or dioxygen gas, what it will do? It will poison the platinum asbestos, which acts as the catalyst in that oxidation process. So, it is known to us earlier. Now, we will take utmost care so that impurity does not go into the solution or go into the gas. But can I guarantee you that it will be completely impurity free? So, any impurity that is present in the gas or in the solution may poison the activity of this platinum electrode. So, these are two severe limitations. The first one is it is not easy to maintain this pressure and the concentration of this H plus ion, the pressure of hydrogen gas and the concentration of H plus ions. And secondly, it must be impurity free, and 100% impurity free is not possible. So, it is going to disturb the functioning of the electrode. That is why we need a secondary reference electrode. So, that must be easy to maintain so that we can experiment with ease. It can make our life simple in the laboratory. So, we can categorize reference electrode as primary. Example is standard hydrogen electrode. This is the example. Secondary, the example is Calomel electrode, which is the today's topic, and there are subsidiary reference electrodes. Examples are silver chloride, which we will not learn due to our limitation, and lead sulfide electrodes, etc. So, we have learnt it. Now, we will learn it in this lecture. So, you can see in the right hand side of this board you have the Calomel electrode. There is a platinum electrode which is into a sealed chamber containing mercury. This one is liquid mercury, and you have a paste of mercury and mercury chloride, and here you have KCl solution. Now, what will be the concentration of this KCl solution? This is the question. Now, depending upon the concentration of KCl solution, we have classified 3 standard Calomel electrodes. We have classified 3 standard Calomel electrodes. Now, first one is the saturated Calomel electrode, and it contains almost 4.4812 normal KCl solution. The saturated calomel electrode contains almost 4.4812 normal KCl solution, and another is normal calomel electrode which contains 1 normal KCl solution, and another is deci normal, that is 0.1 normal calomel electrode. So, calomel electrode, which is the secondary reference electrode, are of 3 types. Since its value is known, we will use this reference electrode to find the electrode potential of unknown electrodes. So, hence it is named as the reference electrode. So, first one is the saturated one. It has a concentration having 4.4812 normal almost, and it is normal electrode, normal calomel electrode. So, it can be referred as the standard calomel electrode, since it is 1 normal, it is having 1 normal Cl minus ions, and the third one is the deci normal standard electrodes. So, this is the structure. You have to construct it in this way, and see, there is no difficulty in maintaining the pressure of hydrogen gas here, and you can port it. So, it has portability rather than this standard hydrogen electrode. Now, how will you use it as a reference electrode? That is a question. In the previous lecture, in lecture 11, I have shown you the purpose of using standard hydrogen electrode, SCE, and the method of using it, and with the help of this standard hydrogen electrode, how we have been able to determine the standard electrode potentials of any unknown electrode. That we have learnt in the previous lecture. Now, since this is also a reference electrode, we must be able to determine the standard electrode potential of any unknown electrode. Now, first let us know the electrode potential of this electrode. This we have to know first. So, for this purpose, to get ready with this reference electrode, first of all what you have to do is to connect it with a SCE. So, this is the SCE. You have to maintain here pressure 1 atm. This is the acid solution. Concentration is taken to be 1.0 normal or molar, whatever may be, no problem, since the valence is 1. Now, the pressure of hydrogen gas is maintained at 1 atm, and the platinum electrode is dipped in the acid solution having concentration 1.0 normal or 1.0 molar, same thing, no problem. This we are taking in the left hand side, and then we are connecting it to the calomel electrode. So, calomel electrode will be this one. See, this is the calomel electrode, it is Hg, then you have Hg2Cl2, and then you have KCl, that is Cl minus. So, it will operate in this way. It is liquid, it is gaseous, it is solvated, aqueous. So, first of all we have to connect the calomel electrode to the standard hydrogen electrode. So, that will be SCE is connected internally with calomel electrode, and then we have to connect them externally with potentiometer. This is the connection. So, this potentiometer will give you the E cell, that is the electromotive force of this combined cell, combined galvanic cell. So, E cell will be, we will use reduction potential. So, that will be cathode minus anode. So, it is E cathode minus E anode, since we are using reduction potential. Now, what is the cathode here? We have taken the Calomel electrode to be cathode and the standard hydrogen electrode to be anode. Since this is standard, it will be E0. Now, this is 0.0 volt. So, it will be ECE, this is equals to 0 at 25 degree centigrade. Now, when we are taking saturated Calomel electrode, that is case 1, when we are taking this saturated Calomel electrode, which is case 1, we are getting this E cell, which is equal to this reduction potential of the Calomel electrode, and we mention here saturated plus 0.2415 volt. So, potentiometer is giving the reading of the E cell to be plus 0.2415 volt. It is not that you are getting it directly, you are connecting it to the standard hydrogen electrode externally with the help of potentiometer. Now, this potentiometer is giving you the electromotive force of the combined cell, and since in the previous lecture it has been considered that the electromotive force of standard hydrogen electrode is 0.0 volt, that is the convention, then we have the expression to be derived as E cell equals to ECE, that is what is the electromotive force of the cell will be the electromotive force of the Calomel electrode. Now, when we take the concentration of KCl solution within the Calomel electrode to be saturated, that is around 4.4812 normal, we get the E cell to be plus 0.2415 volt. So, you see, compared to the standard hydrogen electrode, it has a greater reduction potential. So, tendency to get reduced, it is Calomel electrode greater than the standard hydrogen electrode. So, it has a greater reduction potential. So, you are getting 0.2415 volt. In this way, when we replace this solution by normal solution, what we will get? We will get this E cell. Now, in this case, both are standard electrodes. See, this is one normal, that is 1 molar. So, it is in standard state and we are maintaining the temperature 25 degree centigrade. This is also in standard state. So, it will be E0 cell. Now, also it will be ECE, this will be 0, that is standard Calomel electrode. This is saturated Calomel electrode, this is standard Calomel electrode, minus E0 SHE. So, that will be, now this one is 0. So, it is E0 CE, and the potentiometer reading is found to be plus 0.28 volt. And in a similar way, for DC normal case, we are getting the reduction potential of the Calomel electrode to be 0.3338 volt. Now, let us check whether we are doing it correct or not. This voltage is given by the potentiometer. So, I am writing the experimentally obtained data, and by no means I am finding it using calculator, using some fundamental principles. I am not calculating it. Just I am putting the data that is obtained from experiment when the Calomel electrode is combined with the standard hydrogen electrode. Now, we can check through our physical intelligence that whether the data that is obtained from potentiometer and the reduction potential we obtained thereby is correct or not. That we can do at this position. So, for that you need to know the reaction that is occurring in this Calomel electrode. Since we are dealing with the reduction potential, let us write the reaction in reduction format. So, you know this is in +1, mercury is in +1 state. So, for 2 mercury it will be +2 and here it will be 2 into -1. So, -2 overall will be 0 and it is accepting 2 electrons to give you 2 Hg in liquid form and it is 2 Cl minus aqueous. See, this is the reduction reaction that is occurring in the cathode. Now, we are dealing with 2 concentrations or 3 concentrations. The first one is 4.48 normal, the second one is 1.0 normal. So, we are reducing the concentration of KCl and hence the concentration of Cl minus ions. So, from experiment 1 to experiment 2, what we have done? We have reduced, we have decreased the concentration of Cl minus ions within this electrode. So, that is going to increase the forward reaction, simply Le Chatelier's principle. So, with the disappearance of product, what will happen? The forward reaction will increase to get back the equilibrium constant. So, the equilibrium will shift to the right and will be re-established. So, from when we switch from experiment 1 to experiment 2, we are actually reducing the concentration and the osmotic pressure of the Cl minus ion decreases and the reaction will go forward, and the forward reaction is the reduction. So, the reduction potential must increase. If we decrease the concentration of Cl minus ions, the tendency to get reduced of this electrode will increase. So, the reduction potential must increase. Now, see what is happening. When it is saturated, that is 4.48 normal, the reduction potential was 0.2415 volt, and when we have reduced the concentration, the reduction potential has increased from 0.2415 volt to 0.28 volt, and with further decrease we are getting plus 0.3338 volt. So, it is in accord with the system. Now, we will have no explanation for this absolute value. This is coming from the difference in the electrode potential of the cell, that is electromotive force of the cell when it is combined with the standard hydrogen electrode, and which is measured by the potentiometer. So, at present we are able to determine the electrode potential of Calomel electrode at 3 different concentrations, and if you wish to have the value of standard Calomel electrode, the value is for the second case, which is plus 0.28 volt. So, you have now Calomel electrode. Now, next what is to do? What you have to do? You have unknown electrode, say Mn plus. Now, you know the value of the standard electrode potential of this Calomel electrode. So, if you wish to find the electrode potential of this unknown electrode, you have to connect it with the Calomel electrode. This is your duty now. And then you maintain it at the standard state. So, you keep it activity equal to 1.0 normal and you keep the activity here A equal to 1.0 normal. So, you are taking the standard Calomel electrode, that is experiment 2. So, it will give you E0 cell, that will be given by the potentiometer when you are connecting it. So, E0 cell will be, now this is cathode, this is anode, it is E0 SCE minus E0, see it is reduction potential. So, you know the value of this one, that will be obtained from potentiometer reading, you know the value of this one, since you are using normal Calomel electrode, that is standard Calomel electrode, its value will be plus 0.28 volt. So, you will be able to determine the reduction potential of the unknown electrode. So, in this way it is acting as the reference electrode. Now, see, you have not considered these values through any convention. You have considered the value of the reduction potential of the standard hydrogen electrode through convention, and it was 0.0 volt, that is 0 volt, simply 0 volt. And with the help of that standard hydrogen electrode, you are determining the reduction potentials or the oxidation potentials of this electrode, and using these values you are determining the unknown electrode potentials of any electrode. Now, think why it is secondary and standard hydrogen electrode is primary. We have considered the reduction potential of standard hydrogen electrode to be 0 volt, that we have considered in convention. However, the actual value has been obtained later, but that is not like this, that is purely quantum calculation, and that is for the metal itself, and the electrolytic solution is avoided. So, that we are not ready to discuss. So, this is the convention in which the electrode potential of this hydrogen electrode in standard state has been considered to be 0 volt. Now, if we connect any electrode whose standard electrode potential we want to know, if we connect that with this electrode, we will get the value from the EMF of the cell with the help of potentiometer. That was the point of discussion in the previous lecture. So, that will directly give you the value of this E0 Mn plus M. You will get this value directly using SHE. So, this is the primary reference electrode, but with the help of this one you are first getting the value of this Calomel electrode, then with the help of Calomel electrode you are getting the value of the unknown electrode. So, it is not primary, it is referred as this Calomel electrode is referred as the secondary reference electrode. Now, it has also some limitations, and that has been tried to overcome in some other reference electrodes, and also maybe there are some system requirements which does not allow to use Calomel electrode or hydrogen electrode. So, for that purpose we need some another electrodes that all have been grouped into the subsidiary reference electrodes. So, this is all about the Calomel electrode, and if you still have any query, if you have any doubts, feel free to contact me in the comment section, I will answer you, no problem. So, that is all about the reference electrode, and these three values are known, and you can use these values. You connect the Calomel electrode with the unknown half cell, and using this procedure you can determine the value of the standard electrode potential of the unknown half cell. So, that is the way to use the Calomel electrode. That is all. Thank you.